Well, let's get started on Unit 3. Well, we've got intermolecular attractions. Big part. This is actually, Unit 3 is the largest section, not only by number of sections, but also by percentage on the AP test. And intermolecular attractions are the way to go when you're talking about how a lot of chemistry works, when you're talking about substances. So first things first, the state of matter, solid, liquid, gas, all those are determined by the attractions between particles. Intermolecular is between one molecule and another, kind of like between this attraction and that attraction. As far as the bonds between them, that's intramolecular attractions like we talked about before. So room temperature, moderate to strong attractive forces means it's going to make a solid or a liquid. The stronger the attractive force, higher the boiling point, because that's what something is by a liquid or solid, is based upon the attractive forces between those. There's other factors, though, that influence melting point. So why are they attracted to each other? Well, depends on what we have that is being attracted. If it's ion to ion, those are the opposite charges that are attracting. Polar end to non-polar or polar, also, so positive and negative in the covalent sense. Hydrogen bonding will be really strong. It's intermolecular, it's not bonding, but it's called that. Even nonpolar molecules have temporary charges. So intermolecular is between, big distances. Intra is a close distance. So keeping those apart and separate, making sure you don't say the wrong thing on the AP test is also very key. So why are they attracted to each other? Well, larger charge, stronger attraction, longer distance, weaker. And of course, the opposite of those are true. However, when we're comparing the idea of a bond energy and a intermolecular force, intermolecular forces are always going to be much weaker than bonds would be. Because again, it's much larger distances, generally smaller charges, because even when you have something that's polar like water, these are partial charges, meaning less than 1. So these are going to be much less attracted to each other. Now we have some trends. The stronger the attractions, the more energy it'll take to separate them. Just like bonding, nothing different. Stronger the attractions, the more energy to separate. Boiling requires it that we add enough to overcome the attractions because we go from liquids that are in contact to gases that are separate. So we need to overcome those. We're not breaking any covalent bonds, okay? None. So when you have, just like when you think of you have something that's, I don't like using water all the time. Can't really think of anything off the top of my head. When you have water and it becomes a liquid, you're loosening up those attractive forces. And then when it becomes a gas, then it's going to overcome those attractive forces, which requires energy. So the higher the normal boiling point, the stronger the intermolecular attractions. And when we say normal boiling point, the vapor pressure is equal to the atmospheric pressure. So if we have a different atmospheric pressure on that day, like when we have low pressure systems come in, when we have rain and snow and inclement weather, the vapor pressure actually is going to decrease. So we'll talk later about how this all works together, but we need to be cautious that when we think of when it's out to the open, we're just talking atmospheric pressure, and we're going to often contact or think about it as 1 atmosphere of pressure. So talks of kinds of attractions. A lot of this should be reviewed that you've heard before. London dispersion. These are temporary polarity when unequal distribution leads to attractions. So you got the London, lowest form. Dipole, permanent polarity. So this is when you have the ideas of polar molecules. Structure leads to attractive forces. Then a higher level of polar is called hydrogen bonding. That's when you have a very specific example of hydrogen attracted to nitrogen, oxygen, or fluorine. That is going to have hydrogen bonding. You need to make sure that is different than what you think of as dipole. So when you look at a relative magnitude, kind of putting these together, covalent bonds, kilocalories per mole in the hundreds. Hydrogen bonding, what? That's like 10 times less as strong, 10% of that or less. Dipole, way lower. London, way lower. So just by themselves, this is kind of the order of strongest to weakest in this concept here. But a lot of this, we're utilizing these concepts in order to explain why we see what we see in different situations. So just as a little practice example, when we say predominant, it's like, what's the major factor? H2O. Well, we've got oxygen bonded to a hydrogen. That is going to be hydrogen bonding. Ammonia, NH3, nitrogen bonded to hydrogen. Also going to be hydrogen bonding. H bonded to Cl. Now, those are different molecules. We're going to have different electronegativities, so that would be polar. Carbon bonded to oxygen. You might just go, well, those are different elements. That's got to be polar too. However, that's also going to be linear and symmetrical. So that's going to be nonpolar. So you would say London forces. CH4, also linear, not linear, tetrahedral, but carbon and hydrogen are very close in electronegativity, so that would be essentially London forces. H2S has a similar structure of H2O, so that being known, we would have that to be dipole-dipole. So you can see you need to understand the shape and structure in order to understand if that's going to be polar or nonpolar. Therefore, you're going to have to understand what the intermolecular forces are. So types, we've got these here. These we might have touched on a little bit. Ion dipole, which is a molecule like water often with an ion. Ion induced dipole, this might be occurring out in like gases. And then dipole induced dipole. So all these should be somewhat familiar. And again, we're going to go into a little more depth in the ones down below. Hydrogen bonding, we'll start with the strongest first. So something like ammonia and water, you got this hydrogen bond. We can see that the negative attracts the positive of the neighboring molecule. And the reason this is strong is because these partial charges are high. I don't know, 0.7, 0.8, not like 1 when we have like sodium and chlorine, but also pretty darn high. And so these come between based upon the imbalance of the hydrogen pull of electrons compared to the nitrogen pull. Low electronegativity, high electronegativity. Therefore, this difference is going to be quite high. This is the main concept in DNA. We've got like something like thymine and adenine that you might remember from biology, that the hydrogen bonding part going on here is going to attract that oxygen here. This is again hydrogen bonding, and that all the different types, they're always going to have different components of hydrogen bonding. That's why DNA is pretty strong, but it's only held together by hydrogen bonding, which means it could be unzipped apart and copied. So that creates a very big idea of why DNA works so well. So very electronegative, it's going to have the electrons really pulled towards it, meaning the hydrogen doesn't. Got no other electrons, so it becomes very positive. The nucleus becomes deshielded, exposing the hydrogen proton. Very strong center of positive charge, attracts electron clouds from everything else. So this is the main reason and explanation of why this has such a big impact. Remember, they need to be attached directly, not just somewhere in the molecule, but directly attached to it, because this gives the idea that you have this big difference in electronegativity. A lot more electron density over here, very little over here, very negative, very positive end. So we see this in water and ethanol. Again, which one? Looking at this hydrogen bonding here, you see the negatives attracting the positives. A little more complex here, and we can see that this carbon-hydrogen is kind of like a nonpolar. We often call it a tail, but it's a little small, so it might be like a little snipped tail. But the hydrogen bonding going on here is where you're going to have that strong attraction of the negatively charged oxygen to the hydrogen, this oxygen to this hydrogen. And so we get this very attracted area on this, what's called hydroxyl group or alcohol group. So as we said, it's the strongest. They'll have much higher boiling points and melting than things that don't have it. We'll show you some examples on the other side. But not nearly as strong. You see 2 to 5%, I think I overstated 10% because I didn't take into factor that was 400 to 10. So small amount, but significant. So effective bonding, just as something that is hydrogen bonding, as we talked about ethanol, and then where the oxygen is centered and does not have hydrogen bonding. Same molar mass, same all elements, but look at this huge difference in boiling and melting point. Melting point's a little different because of the fact that it's not as significant, because remember, boiling point overcomes all attractive forces to become a gas. So when you're melting something, these are still going to be highly attracted no matter what size they are. So that's why the melting point doesn't differ as much, but the boiling points differ because of the hydrogen bonding in those molecules. Dipole, taking it a step down. Permanent dipoles, things that we call polar molecules. Again, we know they're polar because of the bond polarity and the shape. So the polarity between the bonds and the shape of it. This will always have an induced dipole. That's what we looked at when we thought about with Vesper. This adds to it, raising boiling points of things that are nonpolar. So it's always kind of like hierarchy. You got your hydrogen bonding, you got your polar, and you got your nonpolar. If everything else was the same, hydrogen bonding is the most, nonpolar is the least. So positive tracks the negative, again showing you a couple different ways that you might see it or orient it yourself. And then the effect there, again, another similar example. We have roughly the same molar masses. We have something that is polar, something that is nonpolar. As we can see, the symmetry of this is great. Melting point, much, much higher for the formaldehyde, and boiling point, much, much higher for the formaldehyde. So the idea, again, those polar attractions are going to be keeping it there, and that's going to have effect on boiling point and melting point. Given, again, the example here is a great one I found online. I think it's actually from our book. So very similar in molar masses. I mean, within a less than 10%. But we look at the polarity of each. So dipole moment is a calculations called Dipole for like quantifying dipole moment. And so we see that the higher the polarity, like actinitrile, yeah, is going to be, more than 100 degrees Kelvin higher than something like propane, which is a gas at room temperature. So gas at room temperature, gas at room temperature, gas at room temperature, gas at room temperature, liquid. So again, these kind of concepts are going to be helpful when you need to explain why is this more so than another. Now we come down to our weakest one, London dispersion forces. London forces, very temporary separations, always found with noble gases and nonpolar. They increase with the size of the electron cloud, not with increased polarizability, I believe. Whew, English is hard. So London forces, the bigger the cloud, the more polar it can be. Don't just say bigger or more electrons. Okay, try to get this phrase down, even though I can't get it down verbally. I could probably get it down on paper. Old Fritz London. Didn't live too long, though. So these electrons aren't stationary. We see them as stationary because we can't make the pages move. They move very randomly, temporary unequal distribution of electrons. So they're always moving, that they're not going to always be the same. Just like my head, one way or another, I lean back and forth, and it can be left a little higher, right a little higher. So this results in a temporary dipole when you have one side having a very low partial, very low positive. These are temporary dipoles. We call them London forces. All molecules and atoms have them. Okay, they're the basis of, hey, electrons move. Temporary dipole establishing one will always induce a dipole in surrounding materials because, again, these things are always attracted or repelled by like charges, repelled by like charges, attracted by unlike charges. So there's always going to be a little bit of this. It's like the kind of gravitational attraction, the idea that everything has gravity, everything's gravity affects everyone else's gravity. It's the very lowest ability for attraction. And you think of these as being so small because atoms are small. So you're going to have a very low amount of attraction, but they can add up. So just like an example, you have this imbalanced here to where we have electrons on the left side and right side. Okay, it's balanced. Okay, it's balanced. Oh, this one's moving around because they're moving in different speeds and areas. Now you're going to have a partial negative and a partial positive part to this atom. So again, very small idea of these forces. Instantaneous on one can induce others as well. So when this becomes in this moment, again, it looks like a snapshot, like it's permanently like there, but again, they're always rotating and moving, that this will be negative, this will be positive. Now that this one has made a positive, that makes this one negative because the electrons are going to be attracted to it because they're free to move, and it can kind of cascade down. So This is always happening in something like helium. And so that's why helium does have some attractive force. It's just not very high in this case. Now let's look into the little less familiar ones that you may not have had too strongly back in chemistry that you had before. Induced dipole. So the magnitude of these induced dipole, many different ideas. This is the polarizability of the electrons. Don't just say bigger mass or bigger size. It's the size of the volume of the electron cloud. Now, generally, more electrons mean larger cloud, more polarizability, I'm getting better, which means stronger attractions. The shape can make a difference too. More surface area, you get a bigger induced dipole, stronger attraction. So that means like big of the molecule. If you have one that's tightly clustered, its surface area is going to be small. If it's really spread out, like long chains of hydrocarbons, that's going to really increase the surface area for interactions. So noble gases. So this is a great example showing the size of the electron cloud, of how that increases London dispersion forces, because they're all atoms. So you could say they're not like a long chain of anything, like I just mentioned the hydrocarbons, but the noble gases are all nonpolar atoms. We can see that the stronger the attractive force is, the higher the boiling point will be. So the idea is that it goes from very small to pretty darn high, even though it's still a gas at room temperature, because of the volume of this. More surface area for polarizability, we will be able to attract more electrons and therefore have partial charges. Number of it increases, more polarizable, which makes it to unequal electron distribution. There's a more likelihood of it being on one side or the other because you have more electrons. If you only have 2 electrons, it's pretty easy to be like, you're here, okay, it's always balanced, oh, slightly different, polarized. If you have and these will have 2, 10, 18, 36, 54 electrons, any one of those being imbalanced, boom, now it's slightly polar. So at any point, it's going to have some induced dipole as you go throughout these. The bigger they are, the more London forces they have, meaning the higher boiling point. So surface area, like I talked about, hydrocarbons. These are both pentanes, meaning 5 carbons and all hydrogens. This one's tightly clustered. This one has a larger area for interaction. This one's smaller. So based upon this being more spread out, this should have a higher boiling point. And when we look at it, got to go back to seeing the other part. Oop, backspace. This is N-pentane. So we think of those long carbon chains. And again, don't worry too much about the naming. That N-pentane would make sense that the more we have, the longer the chain, that's going to have an increment up in its boiling point. Okay, because again of that surface area. Think of the volume of the electron cloud is much larger, therefore it's going to have a bigger ability to polarize. When we think of as intramolecular forces, looking at across these, so these are all in the second period as far as its central atom. And we can see there's a larger variety. Carbon, this is nonpolar, only with some London forces. Here we have our, what do we call them? Hydrogen bonding, much, much higher, even though they're pretty much the same mass or a little bit less. Again, we have something that's the similarity with being a little slightly polar now. This now is all just dipole-dipole. Look at that big dip. Even though their, their electron clouds are larger because these have more electrons, that's a huge dip here. Then we again are increasing because these electron clouds are increasing. So it's going to be continuously getting more and more attractions. But you can see that huge difference very small and early on from our hydrogen bonding going on. Now, ion dipole attractions, this is going to be your common one when you think of solubility of an ionic compound that dissolves in water, because you have an ion floating around, not bonded to another ion, and water being a nice dipole to attract. So, like we've shown in some representations, the positive attracts the negative attracts the positive. The strength is going to be determined based upon the strength between the ions and the ions to the dipole. Now, you also can have ion-induced dipole. So this is something we come across probably the least, So if you have a spherical atom, no dipole. And then if you have a charged ion coming close to it, it can induce a dipole, pulling the electrons closer to it, leaving the other side positively charged. This would be something like if you had, you'd have to around a nonpolar substance. So I'm even struggling to think of one, because even if you have something like, let's say hexane is a very large carbon, hydrocarbon, very nonpolar. If you put a sodium chloride in it, it doesn't break it apart. So therefore, you're not going to have a charged ion. I guess it could be on the outer edge of a crystal that it would make a slightly attracted hexane molecule attracted to it. But again, this is going to make a dipole based upon the positive being there. So it's actually very little used or seen as much as the other ones are. Now, dipole-induced dipole, this happens all the time. This is the basis of why something like water can dissolve oxygen and carbon dioxide, both nonpolar molecules. Otherwise, if it wasn't, none of that would be able to dissolve. You wouldn't have life in the oceans. Fish wouldn't live. It'd be a disaster. So when we have a polar molecule coming around and nonpolar, this is going to pull this side, this is the negative side. This would be pushing the negative electrons away, making this slightly positive, and that's going to have a slight attraction. So this is, again, another slight weak attraction of a dipole-dipole force between something that's nonpolar, between something that's nonpolar and something that's polar. So this is a dipole-induced dipole, right? So careful in ranking. So if you got them just on their own, various molecules we can't get unless we have boiling points and melting points. So this would be something we would show on a test that maybe has a list of boiling points or melting points, and then you're there to explain why you see that, or why is that one an exception, and so on. So if you have a ton of London dispersions, you might have higher intermolecular forces. For example, when we think of all of our different types of liquids that are alcohols, or not alcohols, I'm sorry, your hydrocarbons, they're gases, your propane, your butane, all of those go up. But if you get high enough, you get to something like wax, like paraffin, and that's solid at room temperature. Burns the same, but it's a solid at room temperature due to the fact you get a ton of intermolecular forces. Keep in mind, a lot of weak force could be the sum of a high attractive force. I always like making the reference of like Velcro. You know, Velcro, those little hooks and loops that do it, one of those is super easy to break. But a lot of them can take a lot of force. You've seen those people who like throw themselves onto Velcro things and they get like stuck. If you have a square meter of Velcro on top of a hood of a car, you can lift the car by Velcro alone. So that's where that small weak force can actually create a big one. It'll be more obvious, things like unexpected results, want to consider things strong, weakers ended up being small, weak forces end up being stronger. So there's generally a guideline or an area that they want to focus on. It's common to just list the most dominant. However, it's common for them to want you to list all the forces. So if it's got hydrogen bonding, remember it also has LDF. And so with dipole-dipole, that's already been kind of taken the higher one. But remember, it always has LDF. Look for keywords. You can always go with all of them, unless it says which one was just the dominant. So I would err on the side of caution, giving me all of them, unless it says which one's the predominant or dominant intermolecular force. Also areas to be giving you caution. When to compare two or more molecules, explain why one has the other ones. Mention both. This is a big thing that came up on these kind of common flaws that students do on AP tests. Mention both, okay? It's a lot easier in our common language to just kind of say, oh yeah, he's better. You know, it's like when we talk about sports scores. The A's beat the Angels. That's why I mentioned both. The A's won the game. Okay, A's beat the Angels. You could also say the Angels lost to the A's. So making sure that you say both. As in a good example, you've got both of these. Talk about both. Okay, talk about both. So you've got both of those while saying this has this only because. Discuss both of them. Okay, give it evidence to support your reasoning. So summary, London's the weakest, present in everything. Bigger the polarizability and surface area will increase how much LDFs you have. Polar, dipole-dipole forces. Hydrogen bonding is the highest. intermolecular forces. But again, those are only very particular, and again, with very small atoms per se. Ion dipole, present in mixtures of compounds, polar molecules. When ionic compounds dissolve in water, is, I can only imagine, being the most predominant. Ion dipole attractions, strongest intermolecular attraction. Okay, because an ion to a dipole, that's going to have a huge amount. That usually the only way we can overcome that is either having another ion, which is going to make it precipitate and come out of solution, or get rid of all the water, and then the ions are able to attract itself. That's why when you boil salt water, all the water goes away, you're left with just the salt. Ion dipole attractions, especially important in aqueous solutions, like we just said. So ion-induced dipole attractions. So that's when you have a dipole and an ion that's nonpolar. Okay, makes it slightly polar. Dipole-dipole, when you have things that would a dipole inducing in a nonpolar molecule. So these are very similar. One ion, nonpolar, as opposed to an ion-induced dipole. So again, this is like dissolved in water. This one is when we just have an ion floating around in a nonpolar molecule. Inducing infers the fact that it was nonpolar before. Okay, see, we have induced, nonpolar, induced, nonpolar. Inducing just means to generate, to make, to start. So it wasn't one before, because these are not the same. Again, general ranking. We call them also dispersion forces, London forces, dispersion forces. I don't know why there's so many different ways to say it. Everyone's got molecules for it. Dipole-dipole is only polar, hydrogen bonding's there. Ion dipole is between an ion and dipoles, often thinking of ionic compounds dissolved in water. All right, make sure you come in with any kind of questions. I'm sure you've got plenty. We'll get lots of practice from this, and I hope to talk to you soon. Take care.